好，欢迎大家来参加今天的演讲。我们是很幸运的能邀请到今年的邵逸夫奖得主人来台湾，他是礼拜天就要在香港领邵逸夫奖的正式典礼，所以他就顺路来台湾给我们参访。然后这个礼拜刚好有一个跟这个脉冲星有关的国际会议，所以是很荣幸有这个机会，可遇不可求，这个时机也刚好是今天有经过这里。我认识这位大概才十几年吧，10几年前第一次也是在科学会议上认识他。那个时候，这个快速电波爆还是一个有争议的事情，有多数的人不相信它真正是地球以外来的，大家可能都是认为是地面的干扰啊、微波炉啊各种因素，所以那时候还是很有争议的。那时候跟他们那当然他持续了10几年的不断的研究这个领域，现在近年被证实了，改变了很多地方的研究方向，包括我们现在天文所也是在快速极力的推动一个新的快速电波爆望远镜 Busrts。网上有介绍，然后下一期的季刊也会介绍一下我们在台湾在这一方面要进行的一些研究。我们这里也有好几位我们这个团队的合作者在场，反正有在名牌的大概都是，等会可以有问题也可以问他们。这位Lorimer教授，他是英国他的读大学毕业的，然后在 Magetar 读了博士，也是跟天文大师Andy Line 修了博士学位，所以我们今天给我们介绍这个整个故事的经历。然后我们现在就请Mr. Lorimer please share.
Thank you very much. Really appreciate that. And thank you to Megan for providing the Chinese subtitles throughout the talk tonight as well. It's a real pleasure to be here. This is my first time in Taiwan, and I'm just delighted to be here this week and to be part of this workshop that we're having here in the Institute. And then, on my way to Hong Kong to be part of the ceremony at the Shaw Foundation this year with my two fellow laureates, Matthew Bales and Norman Wilkin. So this is a kind of a dry run of our public talk that I'll be doing tonight. And we have an hour and a half to speak next Monday, and so I'm going to do a shortened version of it tonight. So thank you again for being here, and to want to convey some of the excitement of this field, where we found this new phenomenon, really somewhat by chance, and now it's opened up a whole research field that hundreds of people around the world are making amazing contributions in. So we're going to tell you a little bit about the story of that tonight, and what might be in store in the future. So before I get too far into things, it's worth just resetting ourselves and thinking about how we look at the universe for a moment. Most of our knowledge of the universe comes from this spectrum of radiation here, where our eyes are just able to see the middle part of this diagram in the visible spectrum. What you're seeing is the different wavelengths of electromagnetic waves that travel through the universe and carry information about objects in different ways. So as you go to the shorter and shorter wavelengths over here to the high energies, that's the gamma rays, and all the way down to the longer wavelengths down here in the radio, they all carry complementary information So no single telescope can see all of that radiation at once. So you require a combination of all of these different instruments. Some of them operate on the ground, some of them have to be out in space because the Earth's atmosphere blocks the radiation. Fortunately for us, the gamma rays don't make it down to the Earth. But the radio waves do, and we can observe radio with radio telescopes 24 hours a day. It doesn't matter if the sun's up or if it's raining, the radio waves still make it through. Our optical colleagues, though, have to be on high mountaintops and worry about cloud coverage and things like that and observe at night. But together, and it's very much a huge undertaking, we all work together with our different instruments and learn about these objects and fast radio bursts. Most of what I'll be talking about is in the radio, but what we hope will happen more is that more and more optical and higher energy observations will come as well. But there's already a lot of optical work involved here. So most of what I'll be talking about tonight is in the radio, so it's worth taking a look at the radio sky for a minute. And this is an image of kind of a zoom in on the galactic center. We're not looking at the whole sky, we're looking at the center of our Milky Way galaxy here. This beautiful image that is showing radio radiation. And you can see lots of different features here. There are extended features, like these shells here. There are filamentary structures. There are little point-like objects that look like stars, and some of those are indeed stars, but some of them are background galaxies. The type of stars that we study in radio, that a lot of people are studying here this week, they're called neutron stars, and they are formed in the supernova explosions of massive stars about once a century. One of these massive stars explodes and leaves behind a star that's about the mass of the sun, a little bit more than the mass of our sun, but only the size of a city. So it's this incredibly dense, rapidly spinning object that emits some light, but mostly it emits at other wavelengths. And so one of the ways that we study it is through radio waves. And so again, it's just an example of the different picture that you get by looking at the radio sky. And the telescopes that we observe, these sources, look like the satellite dishes outside of houses, but much bigger versions usually. Here's a very famous one that features heavily in the story. It's the Parkes Radio Telescope. It's in farming country of New South Wales. It's about a 5-hour drive from Sydney. And it's just a beautiful thing to look at, but it's the dish itself is 64 meters in diameter, and as an observer, as someone who operates the telescope, you have a few offices there in the control room, and so you literally sit underneath the telescope and it's moving around you as you're carrying out your observations. I have spent, and many of the people in this room that are visiting this week have spent many hours and days at this observatory and other places like it. And so it gives us a lot of time to not only collect our data, but also think about what it all means. So these are often, these telescopes are often on lands that we're really just grateful for indigenous populations to have been able to use it. And so the telescope is also named Marianne in honor of the indigenous people of Australia. So those are the instruments, and we're looking at radio waves. What we're talking about tonight, in order to really understand where it came from, we have to go back to the 1960s, which was a fabulous time. I was born at that time. That was one of the least important moments of the 1960s. One of the most important ones for astronomers came in 1967, when Jocelyn Bell, who was pictured here as a student in Cambridge in the UK, was observing the sky with a rather strange-looking radio telescope. It didn't look like a dish at all. It's literally just a collection of wires that was strewn across a field in Cambridge. And she and her advisor and a research group were scanning the sky, looking for signals in the FM band. So when you tune your car to FM radio, you still have an FM radio. You're around 100 megahertz. And that's the sort of frequency range of these the signals that they were looking for. And they were basically scanning the sky every day, and then they reconfigured their telescope such that they scanned different strips of the sky as the Earth rotated, such that they could get a map of the entire sky once a week or something like that, every 5 days, I think. And they collected their recordings on pen charts. And so this is a picture of a piece of paper that was just running continually through a printer at the telescope, and it's recording the signals from the telescope. And so what turns out to be a pulsar here is just this little, what Jocelyn Bell called a piece of scruff, just something that was slightly higher than the average noise here. It really doesn't look like much of anything. And in fact, there's lots of interference from man-made transmission as well. And it really took a lot of diligence on Jocelyn's part to look through these miles and miles of chart recording. And she concluded and very robustly showed that this first signal was coming from the same spot in the sky on multiple days. And when they took a look at it with high time resolution, they basically sped up the chart recorder so more paper ran across, and they were able to look at the signal in a bit more detail. They saw these blips here. So each of these downward going pulses is a radio signal that the telescope was receiving that was much greater than the background noise. And so you can imagine it coming like a click like this. And it was happening about once every second, something like I'm trying to do here. That's the spacing between those individual pulses. And so this was very unusual at the time. Normally astronomers are used to looking out at the sky night after night and it being the same. But now we've suddenly found something that's varying on the period of a second. So it's a very interesting story, and the subject of Hall electron itself. Let me give you a quick idea of a picture for you for what these things look like. So imagine that I'm a star, and I am spinning like this on Earth, so that the time it takes for me to go around and come back to you is the time of one of these clicks. So let's see if I can do that. So as I see you, I'll click. All right, so you get the idea now. I'm getting a bit dizzy, so I better stop. But the idea here really is that rather than the star is not making sound waves, what it's doing is it's rotating. But like the Earth, it has a magnetic field, and so it's rotating like this. So this is the North Pole, and this is the South Pole down here. And if the star is oriented such that one of the magnetic axes, or both of them, points to you, then you will see a pulse of emission as the magnetic poles pass your line of sight. What we often call the lighthouse effect. So as you're walking down the beach, you see the lighthouse rotating, with the flashlight beam rotating, and you see that pulse of light. It's the same phenomenon. That's our picture. Except it's coming from a star that is rotating. It's the size of a city, and it's rotating once a second in this particular case, We've now seen them that rotate 700 times a second. And these things are just phenomenally extreme in terms of their physical properties. They have an intense magnetic field, they have an intense gravitational field, and together they're able to, like the combination of rotation and the high magnetic field accelerates particles and produces radio waves and waves across the electromagnetic spectrum that we see. So this was incredible at the time. They actually thought initially that these pulses were from aliens because they were so unusual, and they found a few of them, and they called them LGM 1, 2, and 3. LGM stands for Little Green Man. But they basically pieced it together and saw that they were coming from all over the sky, and they were consistent with a population of objects that was natural in origin, and that's what we see thousands of them today, tracing the Milky Way mostly. So they're amazing, and many of us have spent our lives studying them and have much fun along the way. But we're talking about fast radio bursts tonight. So why am I talking about pulsars? Well, very early on after the discovery of the first pulsar, and once that model of a neutron star was proposed and investigated, the idea is that the pulsar would be formed in a supernova explosion, as I mentioned, and one of the first pulsars to be found was at the heart of this supernova remnant. It's called the Crab Nebula, so it's well known to many of you if you've studied deep sky objects. It's a beautiful object. What we now see is an expanding shell of gas from an explosion that was witnessed by our ancestors about 1,000 years ago, the actual explosion of the star. What we see today is the expanding shell of gas, the sort of the guts of the star, and the core of the star is still spinning. That's the pulsar that I was talking about. And it's spinning, in this case, 33 times a second. I'm not going to try and model that, I would really get in trouble, but you've got something that's spinning 33 times a second, so very fast indeed. And what was remarkable about this particular pulsar was that it occasionally emits really bright pulses as the beam passes by. The emission mechanism was acting in such a way that it produced a really bright pulse that was sometimes thousands of times greater than the average pulse. And astronomers at the time realized that that was a very good way of seeing these objects at much greater distances. This is far enough away to be amazing by itself. It's about 6,000 light years away, but it's in the Milky Way. But astronomers realized that you could place these objects beyond the Milky Way into extragalactic space and still see these bright pulses with radio telescopes. So people were thinking, even back then, about the possibility of detecting these sources. Let me tell you a little bit more about pulsars that we need to know to understand the rest of this talk. There's one quantity that I want you to take home and think about a bit more later on. But it's a concept known as dispersion. We're familiar with the way that the prism spreads out optical light. A similar thing happens for radio waves traveling through interstellar space. So the space between us and the pulsar is not a perfect vacuum. There are free electrons floating around and other turbulent material that many people this week are studying. And in particular, the free electrons act as basically as a prism that has the net effect is to slow down the waves at lower frequencies compared to the frequency that the telescope receives, and this is time. And here's the pulse that arrives it doesn't arrive at all frequencies at the same time, it gets delayed. So we call this dispersion, and we measure the delay. In this case, it's about 400 milliseconds, so just under half a second. That delay is proportional to something we call a dispersion measure. And really what you can think about that is that the bigger the delay, the bigger the dispersion measure, the farther away the pulsars are. So it gives us a way of estimating the distances to pulsars, which is very useful. So the pulsar community was working very diligently over many years, and so now I fast forwarded to 2003, otherwise we'd be here for quite a long time. So I've left out a few details, mostly the history of pulsar astronomy I've skipped over. Really just to say that people were thinking about this for some time, but there were so many other interesting discoveries to be made in pulsars that it took a while for people to actually start to carry out sensitive searches for extragalactic giant pulses, such as the ones I showed you from the Crab Pulsar. A group here at Cornell, Laura McLaughlin, who's one of our fellow Shaw laureates, and her advisor Jim Cordes, carried out a survey of the M31 galaxy, that's a nearby galaxy to the Milky Way, looking for these objects, and they tiled up the galaxy into the different fields that the telescope can see. Back then they used the Arecibo telescope in Puerto Rico. It's no longer with us, sadly, but it was at the time the largest and most sensitive radio telescope. And they looked for these types of pulses. Unfortunately, they didn't find anything. But they made a prediction that really that was just the beginning of what people should be doing. People should be looking all over the sky for these just individual pulses. And so we kept on looking, and a few years after that, this was a project that Nora led in 2006, where she discovered one of these dispersed pulses that I just told you about. So this is radio frequency and time. And so this is just an individual pulse from a pulsar. And you just get one click. Then nothing else happens. This turns out to be a very enigmatic type of pulsar, one that doesn't always radiate. So it goes around like this. And sometimes it forgets to radiate. Oh, there it does one that time. And so it turns out that these are neutron stars that are challenging the way we think about the radiation process. But just by looking for these individual pulses, Nora was able to find an entirely new part of the pulsar population. So this was a really big deal back at the time. We call these rotating radio transients, or RRATs for short. It was, again, an early indication that we really had only started scratching the surface of something bigger that was out there. This is how you look for RRATs and other dispersed pulses. So what you do is you take the data and you look at different dispersion measures. So you combine the data for different delays and make a graph of dispersion measure versus time. What you can think about here really is this is distance, right? Remember, the bigger the delay, the farther the distance. So it's got distance going up here and time along here. And so these little white symbols, that's just background noise. Just coming from either the sky or the electronics in the receiver. And these bigger symbols here, these are detectable pulses. So those would look like these type of things if you made a graph of them in this way. So this is how you look though for pulses where you don't know the dispersion measure, you don't know where they are initially, so you just have to stare at the sky and look. And so this is an example of 3 pulses of a particular dispersion measure. So this was setting things up rather nicely, and what people realized back then was that there was a lot of the universe that we hadn't looked for these type of events for, as I've been saying a few times now. You can kind of summarize that by this graph here. So what you're looking at on this axis is the luminosity. So that's the intrinsic amount of power that the source is putting out. So you think of a 60-watt light bulb. You take that 60-watt light bulb and you go half a mile away, and it looks dimmer when you take it further away, but it's still a 60-watt light bulb. This is just correcting for the distance effect here. So this is the intrinsic luminosity. And what you've got here is basically the pulse width, so how broad the pulse is. And so what we were looking at that time were pulsars. Here are individual pulses from pulsars. Here are the RRATS that were just discovered. They were slightly brighter on average. Here are the giant pulses from the crab. But then there's this whole, and then there's a few really narrow pulses that the crab was emitting, which are really interesting. And then there's this whole space over here of nothing. And so we really we're just not looking at enough data at that time. So we didn't really have any preconceived ideas of what could be out there, and we just knew that we needed to search more data. And so the discovery of the first fast radio burst, which ultimately became known as FRB 010724, or in this case it kind of got my name colloquially. But it actually turned out to be during a search for RRATs in the small Magellanic Cloud, which is this little fuzzy blob over there. There's the large Magellanic Cloud. So those of you who've been to the southern hemisphere, perhaps you can just about see it from here. Not quite. You need to go farther south to see it. These are satellite galaxies from the Milky Way, and they're relatively nearby. So we started looking for pulses in those data, and we enlisted the help of an undergraduate student, Ash Narkovic. He's pictured here with me back in the day, and then this is our family back in the day. So this was just a couple of years after Maura and I got married. We moved to West Virginia, where we still are to this day. And here's our son. We haven't changed too much. We like to keep ourselves. But he's changed quite a bit. He's now bigger than me, and he's almost finished high school. So time goes by, isn't it? But in any case, we started looking for pulses in the Magellanic Clouds, and we were able to do that quickly because thanks to some data that had been collected by some colleagues of ours, including this chap here, Bernie Crawford, the pulsar astronomer who spent a lot of time at that point looking at the Magellanic Clouds, and they put out this paper where they discovered 14 pulsars in the Magellanic Clouds. But they hadn't looked for individual pulses, and so that's where we thought there might be some interest. So we started looking for pulses in the Magellanic Clouds. And our search was pretty much as I just described it. We made these plots where we would look for events that were slightly brighter than the background noise. And here's a particular observation. Look at the amount of time here. It's 7,000 seconds, so just over 2 hours. So the telescope is just staring at a point in the sky for 2 hours. It's a big time investment. And what makes it also pretty unique is that the telescope is able to look at 13 different spots in the sky at once. It has a multi-pixel camera, so your phones have many more pixels than 13. But for radio telescopes back then, 13 pixels was a really big deal. It meant that you could look at a big patch of sky at once, and then spend 2 hours on that, and then go to another spot, and keep on going. So that's what we were looking for, and David Ash was looking for the signals like this in the data. So he and I would meet, and one day came to the office and showed me this huge signal here that was really brighter than anything we'd ever seen. Just to underscore how bright it was, look how puny these little things are. And then suddenly you get this whopping signal that is really off the charts almost, but you can see it getting stronger and stronger at this dispersion measure. Remember, this is distance going up here. So it kind of localizes it to a point in space. And we started thinking about where that could be, and we realized that we were actually looking not just around the Magellanic Cloud, but there was a position or two that we were looking down here that was looking out really into the universe. We were just looking out into empty space. And so we kind of gotten very lucky by a number of measures to see this signal. And it actually turned up in several of the pixels of our camera. I'm going to mark here. The brightest one was turned out to be down there. So that was really unexpected. Here's a plot of the pulse again. It's just so incredibly bright that it was really just had us very, very excited, but also very confused for a while. And you can see this is frequency versus time, so it all happens in about half a second. And the pulse goes down the graph here, as you'd expect for this dispersion, and it arrives later at the lower frequencies. And here's the pulse that results from that. So as we started to piece this together, we said, okay, we're looking at a region of space where we're not looking at the galaxy. We're just looking out into the universe. The amount of delay that we're getting here is way bigger than we would expect from the Milky Way. And so we were coming up with a model, a picture in our mind that looks like this, where the source was actually coming from well beyond the Milky Way, and let's put it in a host galaxy over here. Our best estimates for how far away it was turned out to be up to 3 billion light years away. And so here's an interesting little timeline. So if the signal left the source, whatever it is, this host galaxy, it takes 3 billion years to get here. And so when it was generated, all the frequencies were emitted at the same time. Here's the original pulse. It takes about 30,000 years to get to the edge of the host galaxy. That's long enough. And it gets dispersed a little bit. Then it takes another 2 billion years to get across here. You get, another 3 billion years to get across here. So, and then you get a dispersed pulse like this. Then it enters the Milky Way. It takes another 30,000 years. And then on the 24th of July, 2001, it ends up on the telescope. And we were just happened to be looking at that spot in the sky. It kind of, often with astronomers and scientists in general, we get so into the weeds of what we're doing that we forget about how crazy this sometimes is. There's a signal that was emitted a billion years after the Earth was formed, and then travels, halfway across the universe and arrives at the telescope, and we just happen to be looking at it. So it's an incredible confluence of events that happens. So suddenly we'd seen something really new, and when you add it to that other collection of sources, it's all the way up here. But suddenly we've gone out into this desert and we found something. Because we just happen to be looking at a certain spot at a certain time, we can figure out, how many we're missing. We know that the telescope, only sees a certain amount of the sky. We only look for a certain amount of time, and we actually came up with some estimates that this type of source must be going off a few hundred times every day. Again, that's just a crazy thing to contemplate, that there are these sources going off in the universe, and the universe is big enough and it has enough sources that 200 of them hit the Earth each day that are this bright. It just, again, sometimes you need to sort of stop and think for a second as to this. And so we made some very bold statements in our early paper. But that's what we ended up coming up with. So what could it be? We had something that was, was very brief, apparently coming from very far away, and so we could figure out how much energy it was releasing, and it turns out to be comparable to what the sun emits in a month in terms of its total energy. This thing emitted in a few milliseconds. The same amount of energy. The pulse itself was only a few milliseconds wide, which meant that it had to be coming from something small. Like the whole galaxy can't produce a pulse like that, because the galaxy is hundreds of thousands of light years in size. It has to be something that's able to organize itself on the time it takes from light to travel from one side to the other. So really a few kilometers in size is more appropriate for this type of object. So it's a small object. It's very bright. It's very far away. There are a number of options here. This is an analysis impression of a pulsar that we were talking about earlier on. This is a particularly energetic one known as a Magetar that has a really high magnetic field that emits magnetic flares. Here's another pulsar, and here's the merging of two neutron stars that also produce the energy necessary for that. And here's an airport radar. What's going on with that? Well, again, radio astronomers are plagued by sources of interference, just like optical astronomers have to worry about light pollution. And we were very concerned, as we were doing our checks, that we didn't see, we weren't seeing something that was generated nearby. So that was a great concern for us. But we did our due diligence, and we went through a lot of checks. And as we published the initial paper, we'd essentially ruled out this local phenomenon. But it does pop back into the story briefly in a moment that I want to talk about. So we didn't know what it was, but our best guess was that it was coming from well beyond the Milky Way, and it had a large amount of energy, and it was small. So those are the three things to hold on to. And it's interesting if you go into Google and you Google Lorimer bursts these days, you find some interesting things. It's kind of slowly making its way into popular culture. There is actually a German instrumental post-rock band that has a few albums out, and I've been in touch with them. My sister-in-law went to one of their performances in Germany, and she surprised them. But, so they've been performing under that name. I'm still waiting for the royalty check to come in. And then it also appears in this book about relationships, which is quite interesting. It's like a signal has traveled, through the universe for billions of years to get to you, and so you should be a little patient when you're dealing with other people, that type of thing. So it's a very nice story in chapter 5 of this book about that you might want to check out. But we weren't out of the woods at that point. This was about 2007. And really what had to happen was that we couldn't just, have one object and then be done. We had to, if we're really claiming that this is a phenomenon and hundreds of them are going off in the sky, then we had to demonstrate that by finding more. And so many groups around the world did that, and this particular, one particular search ended up with some interesting objects that kind of had the same general behavior. They weren't always present throughout the band. They had these little blotches, so they looked a little funny there. But they were also present in all 13 pixels of the camera, which was very troubling because it meant it was something that was coming from nearby and leaking into the signal, into the telescope. So these ended up being known as Perytons in the literature. And Sarah, who's now a faculty member at WVU, I remember when she was visiting us years ago, she gave a talk about these. And these are Perytons are mythical Greek elks that cast a human shadow. So it's something that's masquerading as something else. And it was a very worrying time for a while because we had this one object that we didn't see in all of the beams, and it looked a little different, but there were all of these Perytons that were coming around. And so naturally, the community was very, very skeptical. And so where were the other ones? And it took about 6 years really to find convincing evidence for more. And so the landmark moment came about a decade ago. With the discovery of 4 more bursts that are shown here. Here's the original one, and there was another one here as well that was known at the time, but I forgot to add onto this graph. And then these are all the pulsars, and so what you're looking at is dispersion measure, a quantity that we've been talking about, and this is the galactic latitude, so it's the angle that the source is above and below the galactic plane. So these pulsars, this is what you expect for a population in the galaxy. You can see that these sources are clearly very anomalous. And so they became known as fast radio bursts, and they were really presented very compelling evidence now that you have multiple ones coming from cosmological distances. And so when you think about the cosmos, and sources traveling a long way, you have to take into account that the universe is not static, it's actually expanding. And this has been known for a long time, almost a century, since Edwin Hubble showed that the universe was expanding. But what that means for us is that sources can take so long to get to the Earth, in billions of years, that by the time they leave the host galaxy, by the time they get to the Earth, the universe has expanded significantly in size. And so what that does is it not only stretches the distance between galaxies, but it also stretches the wavelength of light, so it makes the wavelength longer. So the radio waves that we receive were actually generated at a slightly higher frequency. And we call that the redshift. Now, it turns out that it's currently impossible to measure the redshift from the FRB signal itself. But if you can find a host galaxy, you can measure its optical light, and from an analysis of that, you can determine what its redshift is and how far away the source is from that. So this becomes a way of measuring the distance directly that I'll show you in a moment. So that's important. Now let me just talk about some of the highlights. Excuse me, that were coming along since then. And this one here came along in 2012, which is the discovery of the The first fast radio burst that was found outside of Parkes was found by Laura Spittler, who was then a PhD student at Cornell, working at the Arecibo Observatory, and she found this source here. That turns out to be really exciting in a moment, but at the time it was just a big relief because it was the first burst that was found outside of the Parkes telescope. So we had more accumulating evidence that these things were really a phenomenon. And then several more came from different telescopes. One from the Greenback Telescope in West Virginia here that some of our colleagues this week were involved in. Some more of them were being found at Parkes. And so we were gradually building up a picture. But you're perhaps wondering, well, what happened to these Perytons? What did they end up being? Well, it turns out that when you microwave your favorite snack, or you heat up your cup of coffee, and you just get impatient and pull the door open, when you do that, the microwave emits an electromagnetic pulse, and it has this dispersive effect as well. And we've gotten to the point at Parkes that various groups had developed a real-time observing system such that bursts could be detected really shortly after they arrived at the telescope. It didn't take us months to go through the data like it originally did. And so we were able to do this experiment. So John here, one of the staff at the Parkes control room, was doing a very scientific experiment. He wasn't touching the microwave himself. He was using his stick. He had the microwave on, and I think somebody was on the other end of the phone line saying, "Okay, John, hit the button," and he did that, and then so he interrupted the signal, and the door pops open, and then a moment later disappeared at the telescope. You can make an interesting graph of the time of a day that these things were seen, under normal circumstances when these experiments weren't being done. And you could see that the Perytons were peaking at lunchtime when everybody was using the microwave. So it was a rather annoying thing that happened because I think it slowed things down a bit, but it was a big relief to finally put this mystery to rest. Anyway, back to the FRBs themselves. That first non-Parkes one that I mentioned a moment ago turns out to repeat. It was the first one to go off more than once. By this time, we'd looked at many of the bursts for hours and hours and hadn't seen anything. And then all of a sudden, this burst started to become active and emitted multiple pulses that were detected. So that suddenly became really interesting because it ruled out, at least for this source, things like explosions or collisions of stars, and perhaps pointed to some sort of recurrent phenomena like individual pulses coming from a powerful object. So that was one big excitement. The next big thing that they could do with this burst was to really stare at it with fine detail. So it's like taking your spectacles off and putting a big pair of binoculars on and looking out at the sky in detail and seeing what you can see. When you do that with a radio telescope, what you do is you add up signals from lots of individual dishes, and you create the effect of a giant telescope that is able to resolve really to look at the sky in very high resolution, so you can see a lot of detail. Kind of the detail that our optical colleagues can see very easily, but with radio waves it's a little bit harder. In any case, they did this. They looked for several weeks at the sky, and eventually found a burst, and they were able to pinpoint it to this host galaxy here. And they were able to measure the redshift of this galaxy, and it turned out to be 2.3 billion light years away. So that was a really important moment, because it showed that definitively that this burst was coming from a cosmological source from a galaxy. So I'm going to, for the remainder of the talk now, I'm just going to go over a few highlights and tell you about a few different things. So these repeating bursts are still few and far between. There are about 60 of them currently known, and that's about 10% of all of the fast radio bursts that are currently known, something like that. So they're relatively rare, and then even rarer still, when they're studied well enough, it turns out that the repeats are seasonal, that they have their kind of their own seasons. What I mean by that is that they become active at certain times, and then they become dormant again, and then they become active again. So the pulsars themselves have a seasonal activity. One has an activity period at every 16 days it becomes active. Another one becomes active every 157 days. But it takes a long time to really to study this type of behavior, and so we're really just at the beginning of this phase where we're really trying to understand, how these seasons work and what they actually mean. So I won't say too much more about that particular phenomenon right now. But you might be wondering, well, if fast radio bursts can go off in other galaxies, could they go off in our galaxy? And the answer is yes. We think that there's an FRB-like source that does come from our galaxy, and it was spotted in the year 2020 using two telescopes, one of which I'm showing here, the other one I'll mention in a minute. This is the STARE telescope, and it's basically an all-sky monitoring telescope, very novel design, but it's looking at the whole sky basically that's above the horizon for very bright pulses. And so what they found was, and this is some data from the other telescope, CHIME, that was also looking at that spot at the time. What they found was that the burst was very bright, sort of 1 million times brighter than the original Lorimer burst. And so you can see it with a small telescope like this. And it turns out that it's connected to a very well-known source in our Milky Way, one of the Magetars, and these are the highly magnetized neutron stars that are known. And two of the Shaw laureates that will be in Hong Kong next week that were awarded the prize a couple of years ago during the pandemic, they will be there. One of them is, both of them are known to this community, I think, but one of them very well known, Vicky Caspi here, is a pulsar and fast radio burst aficionado. Chris Kubiliotto is more of a gamma ray astronomer, and they have made very important contributions to what we know about Magetars. And so, really what I want to say here is that what this provides is some pretty compelling evidence that at least some of the fast radio bursts could be coming from Magetars, which is pretty exciting. So, on to the current telescopes now, just to sort of finish things up. One of the telescopes that's really making a huge impact in the field is finding about three FRBs every day, is the CHIME telescope, and it's the main station is in Penticton in British Columbia in Canada, and it is an unusual design. It's a collection of cylinders that is looking at the sky. And what makes it remarkable is that it can see a large swath of the sky at any given time, much bigger than a typical telescope of the equivalent size, which can only see a small patch of sky. So that allows it to find lots of FRBs, and it's found thousands at this point, which is amazing. And so one of the things it's doing with all of these FRBs is it's giving examples of FRBs in different locations, and you can see one in a spiral arm here, of a spiral galaxy, and another one in a globular cluster system, which is an incredibly old stellar population of another galaxy. So that's really exciting. And the other thing that it's doing is it's giving us strong evidence for multiple classes of FRBs, so different populations. So we're not just looking at one type of object. Remember I told you that about 10% of the FRBs so far repeat. So there's currently a lot of debate about whether they all repeat, or we've just seen the ones that most frequently repeat. But it seems like the repeating pulses are quite different. So what we're looking at here is, I won't get into the weeds here, but really the one-off pulses tend to be short duration, but broad band. They occupy most of the frequency window. And the repeating pulses are longer duration, and they occupy less of the frequency window. So they look very, very different, which is very interesting. And just moving on to some few more results. One also very prolific telescope is in Western Australia. That's ASKAP, the Australian Square Kilometre Array Pathfinder. And it's a collection of small dishes that's able to look at a reasonable portion of the sky, but also localize the FRBs very well. And so it's finding lots of examples of FRBs in galaxies. They often come in quite galaxies where there's a lot of star formation. Some of the old, what are called red and dead galaxies, they're less common, where less star formation is going on. But FRBs, what this is showing is that FRBs are coming in a variety of different environments. And so that's a very interesting piece of the puzzle. I do want to mention one very important result that was made possible by FRBs, and that is to map out the gas between the galaxies. And so we've got gas in the Milky Way, and we've got gas in the galaxies themselves. But the space between galaxies is also not entirely empty, and there are actually free electrons in there that are causing this dispersion. But this group here, using ASKAP, were able to show very conclusively that the dispersion that we're seeing from the FRBs is dominated by the gas in between the galaxies. So this is a very important result because it was one of the first direct measurements of that phenomenon. It was led by a very famous radio astronomer who passed away very tragically in 2020, J.P. Macquart, who led this collaboration. And here's a picture of J.P., and this is a montage of Zoom profiles of many of his colleagues at a meeting that we organized during the pandemic. And so, thanks to his excellent work, that relationship has been established, and it's known as the Macquart Relation in his honor. One final result that's very hot off the press, that's really exciting, is that they've now found an FRB at a redshift of 1. And so what that means is when the FRB was emitted when the universe was half its size, half its current size, and that means it's traveled about 8 billion light years to get here. So, the burst was formed before the Earth was even here, and it's traveled all this way to see us, which is very nice. And the energy that this burst is releasing is quite impressive. Around 60 years of the sun's energy is released by this particular burst. So it's very bright, and it also gives us a clue again that there are many more of them even further away that can be discovered. So, going back to our diagram here, when I was growing up, my mother and father always told me to look left and right when I was crossing the road. I hope you do that too. It's very important. It's also very important when you're looking for new things. In this particular case, by looking left and right, I mean look to the left of this diagram and look to the right of this diagram. So there's still a lot of empty space over here. These would be the long pulse width sources. And then there's a lot of empty space over here. There's a couple of FRBs known that emit very narrow pulses. And so, again, that's surely the tip of the iceberg. But look, you can see that the population of fast radio bursts has now been filled in, and then these are some of the bursts that are seen from Magetars in the galaxy. So there's still a lot of work that can be done here and much to explore. And there's a meeting going on in India online this week, and there's also this meeting that our colleagues are at this week where FRBs are being discussed as well. Very grateful to the community that are working on this now. And I'm not going to get into all these questions here, but things like the community is trying to really establish, how many populations of FRBs are there, and do they all repeat? These seasonal FRBs, how can we learn more about those? Will we ever understand the emission mechanism from FRBs? And that's an ongoing question. And we can use them as probes of cosmology, as we've seen. So it's just a tremendously exciting time, and it's been a tremendous honor and a lot of good fortune to be part of this. I do want to close by thanking our collaborators, Fermi, Corford, and Nationalkovic on the original discovery paper. And really all of our students, colleagues, and postdocs who work in this area and in the pulsars and have just enriched my life, and I know Maura and Matthew's as well. We get so much joy from working with you all. And our big thanks to the Shaw Foundation for recognizing this work. We hope that it will be a catalyst for more discoveries in the future. Our work is really made possible by a number of entities. I won't read them all out here, but just want to recognize that as taxpayers, wherever you are in the world, you are contributing to this effort. Without your support, it goes to government agencies and helps to establish private foundations. That support would not come to us, and we would not be able to do any of the science that we do, all of these facilities that I talk about. They're made possible by you, the taxpayers. So thank you very much for continuing to support this work. Because we believe, in astronomy that one of the things we're trying to do is just promote fundamental science. We know that we're not training every student to be an astronomer. We know that many of our students go out and become very successful in many other fields. The point is we're trying to bring them into science through astronomy. We hope that many of them will stay, but we're really trying to enrich the bigger picture through our work. So thank you very much, and thank you very much for listening tonight. I really do appreciate it.
我们非常感谢Duncan Lorimer 教授今天的演讲。那现在有没有想要问问题的呢？用中英文问都可以。而且问题的话，会有得到他亲笔签名的英文寄报哦。
Yes. Thank you very much for these talks. I have a very basic question. So you showed parameter space, the luminosity as a function of relation, and then you mentioned that there are still many other parameter space that we could explore. That is very amazing. And then I could imagine that the longer time scale would be probably in terms of technology, maybe easier, I guess, because say second or minute time scale is more like our human time scale. So therefore, I may imagine that maybe observationally may be easier to investigate.
Yeah, that's what you would think. It's actually easier to do the short timescale stuff right now. In some ways, it's not neither are trivial, but the long timescale stuff is what you sometimes run into is the stability of your radio receiver. And if keeping that stable on timescales of 10 seconds is challenging. So,
I see.
Yeah.
So that means we actually don't see populations at longer timescale. That means we don't have enough survey in that timescale.
Well, there are some things off to the right here that I haven't even shown, and those are long period transients. they can be variable stars and other types of sources. But what I'm kind of alluding to, without really saying here, is that we know that there are populations of pulsars with very long spin periods that we missed, and so this would be one way to find those in the Milky Way. And some of the white dwarfs in the galaxy could be seen that way too.
Thank you very much.
Yeah.
好，再有其他人要问题吗？
Thanks for a great talk, Doug. I also have a question about this plot. So underneath the Lorimer burst, you're showing that population of basically more generic fast radio bursts. So how do you get a luminosity for each of those? Because I wouldn't have thought that number of them actually have host galaxy identification.
That's right. The most of them though are repeat pulses from repeaters, so they're kind of filled in. But then I think there are some that are estimates. But I think most of those are pretty well determined distances. This is a guess, though it could actually be lower than that.
好，那有没有其他人想要问题呢？
Is there any benchmark to compare faster radio burst and gamma ray burst to compare to the two phenomena.
Yeah, there is. Sorry to interrupt, but I think it's a great question. You're asking, are there efforts to look for connections between fast radio bursts and gamma ray bursts?
Yes.
Yeah.
To come this, there is an example to compare the two phenomena.
Yeah, no, it's a great question, and it's something that is actively being pursued right now. One of the best facilities to do that right now is CHIME, and there's a couple of papers that have come out in the last year or so that have taken advantage of all of the FRBs that have been seen by CHIME. Because what you've got to do is you've got to be looking with two telescopes at the right place at the right time. So you've got to be looking with a gamma ray telescope to find the gamma ray burst, and then you've got to have a radio telescope looking in the same spot. So it's doubly challenging. And so far there have been limits on the brightness, the luminosities, and they turn out to be up here somewhere. We would have seen them if they'd been this bright, but we haven't seen any examples yet. We haven't really been what am I trying to say? We haven't had enough observational exposure yet to really conclusively see if there's a connection. So it's an ongoing experiment.
Thanks.
Yeah, thank you for that question.
Thank you, Dr. Lorimer, for the wonderful talk. I was wondering that, because I've seen in some posters and some scientific articles saying that FRBs currently don't know what their mechanism is. And so I was wondering that whether there is any observations, like here in radio or other wavelengths, that we can conduct to place physical constraint on these objects so that we can somehow try to guess or understand what the mechanism that they are forming from.
Yeah, I think we have a pretty good idea from the radio observations, we know that the sizes of the emission regions, just from the pulse widths, that's a big clue. The one thing I didn't mention at all in the talk is we also have information in some cases about the magnetic field in the environments around the FRBs. So, for example, that one that was first localized to a galaxy turns out to be in a very highly magnetized environment. And that could be playing a role in it. It could be, for instance, a Magetar in orbit around the center of that galaxy and interacting with that environment. But yeah, there's really a lot to be done. One interesting experiment that is going on right now is to look in the optical as well, simultaneously with the radio, because there are actually reasonable prospects for seeing optical emission from some of these brighter sources. But again, it's a very challenging experiment to do. And so the big area right now, I would say, is building up the statistics of the population so that we can study them as an ensemble, and that then we can compare them to other stellar populations. But also look at their environments and see what type of environments they're in. So we know that they're in different types of galaxies. They're in globular clusters. They're coming from a wide variety of sources. So I think that the general thing in people's mind right now is that they're coming from multiple populations of sources, and so that's what we hope to learn about in the coming years.
好，那问题来了。
Hello, I have a question about dispersion measure.
Yes.
So, how can I separate the effects of intergalactic medium or interstellar medium or close galaxy effect of them to estimate the distance between stellar and vast radio burst source?
That's a great question. Let me just pull up a slide to help orient ourselves to that. Basically what we do is we take advantage of what we've learned from pulsars, where we've been able to map out the electron content of the Milky Way through measurements of pulsars. So we have very good models of the electron content there. We know we have reasonable constraints on the electron density in the halo from other observations. And by association, with this being another galaxy, we can again model it based on what we know as the Milky Way. And so what we're left with is this extragalactic contribution here, which turns out to dominate the total DM contribution. And so that's one of the things that we're really studying, and that's what we're learning about. And so when you can constrain this DM-IGM term, the intergalactic medium, when you can find out how much dispersion there is from that and measure the distance, then you get a measurement, direct measurement of really the number of electrons along the line of sight. What you end up with is the electron density. And so what we'll be doing as we find more and more of these is really making a map of the electron content of the universe. So we take advantage of other measurements that have gone before us.
好，那我们小礼物发完了，但是如果还有问题，可以继续发问。有吗？如果
Thank you for the good talk. My question is, you mentioned about the fake noise from the microwave phone. So how do you rule out the signal? Or how do you distinguish the signal from the real FRB and the microwave?
So how do we distinguish the? Yeah. So what we did there was we had it was really a scientific experiment where we timed the opening of the microwave door with the time that the pulse arrived at the telescope. And so we could create these bursts on demand just by continually opening the door of the microwave, right? So you could do that all day, but once you made that connection, you saw that was the source of that interference. So that explains the perytons. What you then have to do is look at the FRBs themselves and say, how are they different, right? And so for the original one, the saving grace that it had was the fact that its main saving grace was it was only visible in 3 out of the 13 beams, not all 13. If it had been in all 13, I wouldn't be here. We would never have written the paper. So the other thing that it had going for it as well, which is getting into the weeds a bit, but the pulse evolves with frequency in a way that implies that it's traveled through a turbulent medium. That's unlike an interference signal that's just come from nearby. So it's those two pieces that you put together and you say, okay, there's no way that those sources are anything but celestial. And then it's really nice when some of them repeat, right? Because you can go back to that spot in the sky and you know that they're going to go off again. So it all starts to just add up different lines of evidence.
好，那有其他问题吗？
I just wonder, it is possible for radio telescope to do sky survey and establish maybe SRB map and may predict some certain region that may occur FRB and for us to pay our attention to this certain region.
Yeah, that's exactly what's being done. It's a great question. There are a number of telescopes that are really doing FRB surveys. What they find, and so there's one here that's being built in Taiwan that will be operational in the next couple of years that will be doing its own survey. But one of the things that is being found already is that once you take into account the exposure of the telescope, let's say CHIME, this one in Canada, you conclude that they're uniformly distributed on the sky. And so again, that's what you'd expect for a population that's very far away. They have no knowledge of the stars in the Milky Way. They're just coming from random directions on the sky. And so really, that's the best observational strategy. If you have a large instrument and you want to find more FRBs, you just point it wherever the telescope happens to look, and you have as equally good chance as looking there as elsewhere. But your question also raises an interesting point as to maybe you could target, now that we know a bit more about FRBs, we think they come from Magetars, perhaps many are formed in globular clusters. What we can also do is look at nearby galaxies and really give those a hard stare, like Winnie the Pooh, if that's, not Winnie the Pooh, no, Paddington. maybe that's lost on the current audience, but really look at the individual galaxies and have a stare at those and see if you can find more in there where you might expect there to be more of them. If that makes sense. So really, the two strategies are complementary. So you do these targeted searches, and then you also just keep looking at the whole sky. Both of them work.
Hi. It is possible to find some FRB which is aligned with the disk of the Milky Way. So maybe we can use this property to maybe figure out some profile of the dust in the Milky Way, or the dust is like like or FRB cannot penetrate the disk of our Milky Way?
No, it's an interesting point. What is found actually is that the material in the Milky Way is, and many of the people here this week are experts in this, but the material in the Milky Way is modulating the signal of the FRB such that it's twinkling. So those FRBs that happen to pass through sort of close to the midplane of the galaxy are modulated by the galaxy itself. They're not completely obscured generally, but they do. The galaxy does play a role. Yeah. So all of these issues have to be taken into account when you're trying to determine the underlying distribution of them. But yeah, you can study the effect of the Milky Way that way. You can also look, of course, now that we know that there are examples from a magnetar, is to look for FRB-like pulses coming from the disk within the disk of the Milky Way as well. And those experiments are ongoing.
Thank you for the amazing talk. And my question is, if we can we tell the type of the source of FRB, such as black hole, neutron star, or twin star, based on the pattern of the radio signal received?
Not yet. So what happens is when you calculate the amount of energy that's released, there are many different combinations of sources that you can come up with that will do that. So black holes, if a neutron star, let's say, collapses to a black hole, for example, say you just keep dumping matter onto a neutron star and it collapses to a black hole, then it will suddenly boom and turn into a black hole, but its magnetic field will be like the rug's been pulled out from under its feet. The magnetic field will just be sitting there and it will emit an electromagnetic pulse. So those have been theorized to exist. Those are called Blitzars. So that's one example. You can have merging neutron stars where their magnetic fields interact with each other. That will produce an electromagnetic pulse. And so it's the details then of can we infer what the properties of the source are from the pulse itself? It's quite difficult. There are some clues though that are coming from the repeating FRBs that I didn't really show in the lecture tonight. And that's some of the morphology, the shapes of the pulses are very reminiscent of the radio emission that we see from magnetars. And so that's again suggestive that magnetars are really one of the strong candidates for FRBs. But there might not be enough of them to explain all of the FRBs. It's probably just a combination of different sources. So yeah, that's one of the open questions, really. There used to be way more theories than FRBs. Now there are more FRBs than theories, but there are still a lot of theories. So.
Thanks for the very interesting talk, and it will be related to all previous questions, but I wonder which kind of FRB or which FRB are you want to find in the future?
Oh, that's an interesting question. Which FRB would I want to find in the future? I think what I'm really interested in, it's two things really. I'm really interested in the FRBs in the globular cluster. So there's only one so far, and it looks like it has a very interesting connection to young neutron stars that we see in our own globular clusters in the Milky Way. So that's pretty interesting, and there is some that really lends itself to doing targeted searches in nearby galaxies, and so that's something that we're going to be trying to do. The other thing that I'm very excited about, which we've also mentioned a little bit in the questions, is the possibilities of finding really long period pulsars through individual pulses. I think that's an area that's wide open for more discovery.